Swayam Prabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 2 Vapor Power System Part 2. So, in this lecture number 5, we will try to focus on rotodynamic machines, impulse principles, velocity diagrams. So, prior to this lectures, we have seen that how the steam power plant is being used for power generation systems. Now, one of the integral component of this power generation system is the turbine, but this turbine is considered as a rotodynamic machines, and these machines have certain characteristics. So, we will try to emphasize under what category does this steam turbine fall, and then based on that we will try to classify these turbines in mainly in two aspects. One is through impulse principle, other is through reaction principles. So, the reaction principle based turbines or reaction turbines will be touched upon in the subsequent class, and in this lecture we will specifically focus on impulse principles and velocity diagrams, and we will try to see how these principles helps us in generating power by using steam as the working fluid. So, let us give some brief introduction about the rotodynamic machines. So, this word rotodynamic machines comes under the broad roof of when you talk about fluid machines, when you talk about compressors, turbines which are used in the gas turbine power plants. Again we are also used in the hydraulic power plants. We have impulse turbines, we have reaction turbines, like we have impulse wheels or Pelton wheels, then we have Francis turbine, we have Kaplan turbines. So, these are the terms that are used when you are using hydraulic machines, but all of them falls under the common roofs because they are rotodynamic machines. While rotating, either they produce power or they produce pressure head. So, these are the two categories these rotodynamic machines work. So, basically speaking, a rotodynamic machine means it is the one in which fluid flows freely through an impeller or rotor, and during this motion what happens that there is a energy transfer between the fluid and rotor, which happens in a continuous manner. So, as a result there is a change in the angular momentum of the fluid as the result of torque on the rotor. There are two possibility cases in this situation we have. The rotor can transfer energy to the fluid or fluid can transfer energy to the rotor. So, these two, based on these two we say whether it is a power consuming device or power producing device. Now, when the energy is transferred from the fluid to rotor, that means fluid is carrying a substantial amount of energy and that energy is being utilized in rotating the blades of the rotor. So, then it is known as a turbine. On the other hand, if the energy is transferred to the fluid from the rotor, then the machine is referred as fan, compressor or pump. Normally fans are used for small pressure differences, compressors are used for large pressure differences, and both fan or compressor they are mainly used for gas, fluid as a gas, whereas for pump the word pump is being used when you are using liquid, when you want to increase the pressure head of the liquid. Rotodynamic turbine is also classified by the direction of the flow of fluid relative to the rotor through which the angular moment of change is achieved. So, these fluid directions can be either parallel to the axis of the rotor or in the radial direction or in the mixed mode. So, basically speaking, here if you look at this figure shows that we are trying to concentrate on a steam power plant which is composed of boiler, turbine, condenser and pump. We are now focusing on this turbine component or to some extent pump component, but mainly we will be focusing on the turbine component. And this turbine fall under the roof radial flow machine or axial flow machines. What happens in a radial flow and axial flow machines? We can see here. So, in both the cases there is a these machines are normally classified the way by which the flow direction is done, flow direction is achieved with respect to relative to the rotor positions or the direction of the rotor. So, on that basis we can have axial flow machines or radial flow machines. So, this figure shows the schematic diagram of an axial flow machines and radial flow machines. So, what happens in a radial flow machines? As you see the cross section, one of the cross sections. So, if you say this side view, what happens? The flow comes axially and it tries to pass through the impeller, and impeller consists of number of blades, and this energy from the fluid is taken away by this impeller, and finally the fluid comes as a outlet. So, what we see here is that in a radial flow machines, the flow across the blade involves substantial radial flow component at the rotor inlet, exit or both. But when you refer to the axial flow machines, what happens? A majority of the component flow comes in the axial directions. So, that is the basic difference. So, they are termed as axial flow machines. In some cases, we can have a mixed flow machines. Normally, this happens when we are using liquid, that means in water, particularly in hydraulic turbines, we can have a mixed flow machines, because purely axial or purely radial is almost difficult to have. So, mixed flow machines are already considered. So, in that case the velocity components may have both radial and axial directions. So, another way of looking at our philosophy or viewpoint, that we will be looking mainly on steam turbines, and these steam turbines are mainly referred as the axial flow machines, but they are based on two fundamental principles. One is impulse principle, other is reaction principle. So, accordingly we call them as impulse turbines or reaction turbines. So, in our subsequent lectures mainly our focus or attention will be focused towards impulse and reaction turbines and their analysis. So, the analysis is done in two folds. One is based on the rotodynamic principles, other is based on the thermodynamic aspects. So, both we are trying to link up that what is the efficiency that we get while producing the power. So, let us start the first one, which is impulse turbines. So, before we go for the impulse turbines, we will try to focus on the fundamental principle what is called as impulse. The word impulse normally refers is the very short duration forces, that means a force comes instantly and it dies down. So, how to explain this impulse principles? For that reasons we consider a horizontal fluid jet which impinges on a fixed plate, and what happens? This fluid jet has velocity Vs and it is moving in the positive x directions, and this plate is fixed. So, obviously, when the jet comes and hits it, and since the plate cannot move and it tries to deflect. So, deflection normally the direction almost 90 degree to this plane and from the both sides. So, obviously, this whatever energy it gets carries, since the plate is not moving. So, there is efficiency of the jet or kinetic energy of the jet is almost vanishes or goes as a loss. But in other scenario, let us see that if you relax this fixed conditions, so that means we can make these things that plate is moving. So, how do you make this plate moving? So, you keep this plate stand on a roller, and that roller is such that fixes this blade or plate, and when the jet comes and impinges, obviously the fluid will deflect as well as this roller will also move, means that plate will also move. So, let us see that if you say that the plate velocity is Vb, and that means this Vb is initiated due to the fluid jet when it impinges on these things, and side by side the fluid also deflects. So, let us think about how much force we are applying and how much energy is being transferred. So, since this plate is moving, that means there is work is done by the fluid on the plate. So, let us calculate them by a simple fundamental principle what we call as impulse principles. So, by knowing this velocity of fluid jet and velocity of the plate, what we can first find out is that force or impulse imparted on the jet will be F is equal to m times Bs, and if it is in a fixed case. But if it is in a moving plate, then since plate is moving, so difference in the velocity, that means relative velocity comes into picture. So, Bs minus Vb is nothing but the velocity of jet relative to the plate. Now, moving further, we will try to see how much work is being done. So, referring to the same figure, we need to find out what is the work done per unit time. So, we know this that is nothing but force multiplied by velocity, and this term comes as m dot Vb into Bs minus Vb, and because of this this is what the work done per unit time, that is W dot. But this work is being achieved from the fluid jet which has initial power, which is nothing but your kinetic energy, and that kinetic energy is nothing but half m dot time Bs square. So, we have calculated the work, we have calculated the initial power, then we will be now in a positions to define the efficiency of the plate. So, this efficiency of the plate can be defined by the ratio of work with respect to initial power. And so, by taking this ratio W dot by kinetic energy, we can arrive at these expressions. So, basically taking this ratio, we can arrive at these expressions. But under what conditions this work done per unit time will be maximum? Now, we will be trying to find out. To find out that, we have mathematical expressions that to find out optimum plate velocity that maximizes the power. To do that, we can differentiate this work done per unit time with respect to plate velocity Vb. So, by differentiating this, that is dW dot by dVb is equal to 0, we can arrive at expressions m dot into Bs minus twice Vb is equal to 0. This gives the optimum blade velocity Vb as which is Bs by 2. That means, the fluid jet of Bs, I mean maximum or optimum velocity for when the power is maximum is should be Vs by 2. And for this optimum velocity, the maximum power that we can achieve is 1 by 4 m dot into Bs square. This we can achieve by that putting V optimum speed on this work expressions, we can find out the maximum power. Now, at this optimum plate velocity, we can also find out the maximum efficiency of the plate. This can be achieved at about 50%. So, this gives an indication that from a fluid jet having kinetic energy of half m dot time Bs square, only 50% of the energy is being utilized to achieve maximum power, and for which the blade velocity is or plate velocity is half of the fluid jet velocity. But still there is a question mark, enough energy, what is how we can improve this. That means efficiency, of course, we can go for maximum power, but efficiency is less. So, to do that, let us try to change the configuration of the plate. So, for that what you change this configuration of the plate is that from this plate shape we can imagine to have a curved surface. So, instead of plate we will just say the blade. So, what does this do is that, so here if you see that Bs when it impinges it spreads on both the directions, but here we will try to see that the fluid jet enters the blade in a curved blade and try to come back. I mean the fluid jet also reflects or comes back in a particular direction, in a particular concise manner. So, to do that, let us see if you can improve this efficiency or you can increase this power. So, what we have observed here, that instead of a flat plate, if you take a cylindrical blade that allows the jet to reverse its directions, and this blade is considered as frictionless, so that there is neither expansion or contraction of the fluid from entry to exit. So, basically that we are allowing this fluid jet to travel in an organized manner. Just it enters at this point, we say it is a inlet, and it leaves this blade and we call it as a outlet. So, basically this is in a organized manner. So, through this process it is possible to calculate the impulse on the blade, power and blade efficiency, and further optimum velocity also can be found out, that gives the maximum power. In this case also we will follow this analysis, that optimum velocity will be half of the jet velocity, which is same as the flat plate, but the maximum power will be twice this of the flat plate, and also this equals to the kinetic energy. So, in other words, we can achieve 100% efficiency. By doing so, let us see how we can prove this mathematically. So, for that reasons, we also consider the same philosophy, that we say Vs is the velocity of the jet in the horizontal directions, Vb will be the velocity of the, instead of plate we write that the blade in the horizontal directions. So, relative velocity of the fluid at the jet entry would be Vs minus Vb, since the blade is moving at Vb. So, relative velocity will be at the entry and exit will also be same. But then what will happen to absolute velocity? So, the absolute velocity at the exit would be Vb minus this relative velocity. So, absolute velocity at the entry is Vs, but absolute velocity when it leaves is Vb minus of minus Vs and minus Vb, because the jet turns the direction opposite, and we are looking at the blade velocity in positive x directions, and with respect to this positive x directions, fluid jet moves relative to this. So, which means that we will have absolute velocity at the exit will be twice Vb minus Vs. So, we know the inlet and exit velocity of the fluid, we can find out the what is the rate of change of force, momentum, that is force, that we can find out as twice m dot into Bs minus Vb. So, in the same philosophy we can find out the also work done. So, here you see that the force becomes 2 times that from the previous value for the case of simple plate. Then work done will be twice m dot into Vb into Bs minus Vb. Same logic, we initial power of the, for same fluid power, the kinetic energy is half m dot time Bs square. So, ultimately we will be able to find out the blade velocity. So, eta b will be w dot by kinetic energy. So, by taking this ratio we can arrive at the expressions that eta b or blade efficiency is equal to 4 times entire bracket Vb by Vs minus Vb by Vs whole square. So, we can now able to differentiate the work done W dot with respect to Vb to find out the optimum velocity that maximizes the power. So, this gives a conditions that Vb will be Vs by 2, optimum velocity remains same as that of flat plate, W max is half mv Vs square, but earlier it was 1 by 4 m dot into Vs square, which means that if you just compare kinetic energy of the jet and maximum power, they are same. So, obviously efficiency of the blade is 100%. So, it means it gives an indication that it is possible, theoretically it is possible that entire kinetic energy of the fluid can be converted as for to arrive at work done on the blade if we can align the fluid jet in a cohesive manner or in a organized manner. So, this particular philosophy was utilized to generate continuous power. So, here what we have shown this figure is that the concept of this simple curved blade is extended by using a series of blades arranged in an organized fashion. But what is the basic difference is that, and here the gap between each of the blade is utilized where the fluid jet is supposed to pass. Now, through these things what may happen is that, so in a single blade it is possible to deflect the fluid jet in a completely opposite directions. But since there are finite widths of the blade, and when we have a large number of blades or series of blades, they have to be mounted in certain finite widths of the rotor, and of course, we also have to see that the fluid passes and it moves smoothly in this passage. So, it is almost impossible to achieve 180 degree deflections. So, one particular angle, and in practical cases the deflection is always less than 180 degrees. And of course, we cannot again hit the tip of the blade. When you make this theta as 0 degree for all the series of blades, we have to keep some angle theta, and this theta we call this as the entry angle of the fluid jet into these blades, and many times you refer this as a nozzle angles. So, what I have explained here is that continuous power can be obtained by incorporating series of cylindrical blades mounted on the circumference of the wheel, so that face of the jet continuously rotate the wheel. But then a high speed jet needs a nozzle, that means to achieve this fluid jet we require a nozzle, and of course, it is almost impossible to fix the nozzle. So, that gives the fluid jet at 0 degree value of theta, and that will cater all the blades. So, for that reasons a shallow angle is theta is maintained, and that is with respect to horizontal direction of the jet. And of course, we cannot achieve 180 degree deflections. So, the practical blade turn angle is less than 180 degree. Now, moving further, to extend this impulse principle, if you want to really find out the how much power or efficiency of the blade which we are going to get, then what you do see here is use the principle of impulse momentum concept, which says that work done on the blade can be found out by the force in the direction of the blade, which is equal to the change in the momentum of the fluid in the direction of the motions. And the component of the stream velocity in the direction of the blade motion is, we call this as a velocity of whirl. So, for that reasons what we require is that velocity vector diagrams. So, we consider a single blade and try to find out the velocity diagrams. So, here we refer that when the fluid jet comes and hits, so this is what we say inlet velocity triangle, and this is outlet velocity triangle. If you see this blade direction is BB and fluid the angle at which the jet impinges, that is theta, what we see is the relative velocity Vr1. So, for inlet condition we use the word 1, for outlet conditions we use the word 2. So, let us analyze that when, since the blade is moving, what we see is the relative velocity Vr1, and the absolute velocity of the fluid jet is Vs1. The net effect between these two velocity is the Vb, which actually the blade velocity. Now, again similar to this, what we see, since the blade is moving, we see the relative velocity of the fluid that leaves as Vr2, Vb is the same blade velocity, and Vs2 is the absolute velocity of the fluid jet. Now, what we do here, we include this angle, and typically one is theta, which is referred as a nozzle angle, other is phi, and phi is nothing but is the angle that between Vr1 and horizontal directions. Another angle is gamma. So, gamma is with respect to horizontal, and in the outlet triangle with respect to relative velocity fluid at the exit. Then we have another angle delta, that absolute velocity of the fluid at the exit that makes with the horizontals. Then what you do, you try to put them in a single plot, or you try to merge them. So, there could be two possibilities. One is this delta can be less than 90 degree or delta can be greater than 90 degree. So, ideally speaking, when you analyze these velocity triangles, we will come back what is the significance of these two things. Mainly this delta value will detect whether your work output will be maximum or not. So, what we are now trying to see here, with this information of theta, gamma, phi and delta, we need to create the shape of the blade in such a way which maximizes the work output or work done by the blade. So, how do you do that? So, for that reasons we have to find out what is the force imparted in the direction of the motion of the blade. So, that is always we see that positive x directions, when you say V B direction is this, that is positive x direction we always refer. So, by looking at these velocity diagrams, we can find out that force imparted in the direction of the motion of the blade would be m dot into V s cos theta, which is this component, minus B s 2 cos delta. So, here if you say this particular figure, so B s 1 and B s 2 they are in the same directions, but if you look at this particular figure, we have B s 2 and B s 1 they are in opposite directions. So, that does not matter to us, because this delta will take care whether this quantity is a positive or negative. So, basically speaking, in order to have maximum impact of this force, the entire quantity has to be added up. That means, your delta value should be such that if the cos delta becomes negative, then this term gets added up. So, obviously, since we call this as a wheel velocities, so we write them as B w 1 and B w 2. So, this wheel velocity that has to be added, so that the force will be higher. So, this is the philosophy of designing the blade. Then using this velocity triangles, we can find out what is the V w 1 wheel velocity at the inlet and at the exit. We also can find out what is the relative velocity of the fluid which is entering and exit from this blade directions, in the direction in the positive x direction. So, now once we are able to find out the force, then we can find out what is the work done per unit time. This is again multiplied by force into velocity, that is V b. So, we can find out initial kinetic energy of the jet also half m b b s 1 square, that is the kinetic energy at the inlet or entrance. Now, we looking at this, then we can find out the, by knowing work done per unit time and initial kinetic energy, we will be in a position to find out the blade efficiency by taking this ratio. So, here I have already mentioned that whether the term cos delta is positive or negative, that depends on the what is this angle. So, ideally while doing this design of the blade, one should ensure that entire term, that work done term, that V s 2 cos delta, that means the angle delta should be chosen in such a way that this gives an additional term to the work done per unit time. So, this will be more clear once you solve this problem by using these velocity diagrams. So, once we have force, then we have work done per unit time, then we can calculate the initial kinetic energy, we are in a position to find out the blade velocity. So, the next step is to find out what is the optimum blade speed and maximum work and maximum efficiency. For that reasons, again we have to use the same expression, that is work done per unit time and kinetic energy, then we have to find out the blade efficiency. Then for optimum blade velocity, we must differentiate this work expression with respect to V b, and this gives the optimum blade speed would be V s cos theta by 2. So, here if you recall our earlier expression, that is it was V s by 2 in a curved blade or in a flat plate, but here since it is the jet is impinging at an angle theta. So, it becomes V s cos theta by 2, and correspondingly it gives half m dot into V s cos theta square, and this here maximum work refers to the optimum blade velocity. And finally, we can find out maximum blade efficiency. So, maximum blade efficiency we can find out, take the ratio, we say it is a cos theta whole square, which means if theta is 0, means at 0 degree nozzle angle we have maximum blade efficiency. This is the theory what we get for the simple single core blade. Now, another point I need to emphasize, many times we consider this term phi is equal to gamma, just to emphasize the fact, so that relative velocity at the inlet and exit remains same. So, this particular condition is called as a symmetric blade. So, there is no loss of velocity coefficients, that means during this there is no loss of relative velocity from the entrance to the exit. So, this is another design criteria, and of course, exit wheel velocity is 0 and absolute velocity is straight in the exit direction. This is what it means. Now, let us understand the velocity diagram in a different perspective in terms of thermodynamic effects. So, here what we have done so far, using the rotodynamic principle or velocity diagrams, you try to emphasize how much work we are going to get. But the other side of the thing is that fluid has when the steam comes, it comes with certain energy associated with it, because it is a superheated steam. It has a very high value of enthalpy. Now, how that enthalpy we are trying to correlate with this rotation of the blade. So, for that we find that work transfer per unit time by using these thermodynamic equations as enthalpy difference H1 minus H2 into m dot into Bs1 square by minus Bs2 square by 2. Now, this enthalpy difference typically, since the blade is rotating, so instead of absolute velocity we see this relative velocity. So, by putting this one, we can write this W dot as m dot by 2 into Bs1 square minus Bs2 square, and then we have Br1 square minus Br2 square. So, this is the actual expressions that we are going to get. But ideally speaking, what we see here, because of this rotation, this relative velocity term reduces the work. So, which means if you want to maximize the power, this relative velocity difference components has to be totally removed. So, for that reasons we introduce this concept that if it has to be purely impulse, that means you design the blade in such a way that will have negligible difference in this relative velocity components. So, that turbine will be called as pure impulse turbines, and where absolute velocity of the fluid takes the dominance. So, this is the concept of looking for a pure impulse turbines, and while designing the blades, it has to be ensured that this difference should be as minimal as possible. Now, to account for whether it is a pure impulse or not, we define a term called as velocity coefficients that takes the ratio, that is Kv is equal to Br2 by Br1. So, the impulse turbine blade with frictions, that means if there are some frictions, obviously there will be a relative velocity difference between the inlet from the exit to entrance. So, we introduce a term what is the tolerance level, what velocity coefficient we can assume, that is one aspect. Second aspect what we can say is that we can find out the energy which is being carried by the fluid, that is nothing but the enthalpy drop of the fluid when the energy is dumped onto the blade. So, that is m dot into delta Hs, that comes from separately by which the energy the fluid carries, and that is being transferred in getting this work. So, the ratio between these two, that means we call this as a stage efficiency, which is defined as the ratio of work transfer through the blade divided by the total enthalpy drop of the fluid for entire stage. Stage means that includes nozzle as well as blade. So, in our previous case we said that nozzle is the integral part of the blade because it supplies the fluid onto the blade. So, entire stage, that is the reason the entire stage means it includes nozzle as well as the blade if the fluid were isentropic. So, this is all about you need to discuss. Now, we will try to solve a numerical problems based on our discussions. So, till this point of time we are clear about the impulse principle, we are clear about the velocity triangles at the entrance and the exit. Now, based on this philosophy, we are trying to solve this problem. What it says is that the steam enters the nozzle at an angle 20 degree for an impulse turbine at 30 bar and 320 degree centigrades. Exit condition is 15 bar. The mass flow rate of the steam is 45 kg per second and nozzle efficiency is 90%. The blade is symmetrical and it travels optimum velocity with velocity coefficient of 0.97. It means that blade is symmetrical and due to the frictions only there is a hardly loss of 3% of velocity from the entrance to the exit. So, we need to draw the velocity diagram first. Now, after drawing this velocity diagram, we have to calculate the following parameters like blade angles. The blade angle, I mean the tip of the blades. So, they are in the angles, that is gamma, delta and phi. Power delivered by the turbine per stage and blade efficiency and stage efficiency. So, for that reason we have if you recall our diagram like this, already I have explained Vs1, Vr1, Vb. Angle between Vs1 and Vb is theta, angle between Vr1 and with horizontal direction is phi. Similarly, this is your inlet, and at the exit the angle between Vs2 and horizontal is delta, angle between Vr2 and horizontal is gamma. So, while by merging this, these are the angles, but to analyze the velocity diagram in a different way, we have to merge to these two diagrams. But before you do that, first we need to find out what is about the steam conditions. So, for that we have to recall our study that either you draw temperature entropy diagram or enthalpy entropy diagram. We see that the steam that comes somewhere at from the nozzle, and had this process been isentropic, it would have come back to this S, that means isentropic process, otherwise it is coming at as S1. And at these conditions, that means this particular condition is 30 bar and 320 degree centigrade, and exit condition is 15 bar. So, this pressure is 15 bar and this pressure is 30 bar. So, we have to use our previous study or concept to find out the steam conditions. So, solution you start with, first thing you need to find out what is this Vs1. So, Vs1 information will come from this nozzle efficiency and enthalpy drop. To calculate this enthalpy drop, we need the steam conditions at the nozzle end, at the inlet of the turbine and the exit of the turbine. So, at the inlet, or you say steam condition leaving the nozzle, we say that is 15 bar, and entering the nozzle bar 320 degree centigrades. So, at these conditions we can say Hn, that is inlet conditions, that is at 30 bar and 320 degree centigrade, the steam table gives 3043.4 kilojoule per kg. Of course, we require Sn, that is enthalpy at the nozzle end, that value is 6.6245 kilojoule per kg Kelvin. So, once we have this Sn, we can say Sn is equal to Ss, that means at this stage is process is isentropic, and that number will be 6.6245. Now, at the leaving condition, condition will be now 15 bar and entropy 6.6245 kilojoule per kg. So, this condition will give you this enthalpy value as 2899.3. So, then we have nozzle efficiency definition. We can write Hn minus Hs1 divided by Hn minus Hs, that value is 0.9. So, we have Hn, we have Hs, what we do not know is actual condition that leaves the nozzle. So, this will give you Hs1 as 2913.7 kilojoule per kg. Then Vs1 is nothing but twice times delta H, square root of delta H, that is twice into delta H means 3043.4 minus 2913.7 into 1000 because it is in kilojoule. So, this will give you Vs1 as 509.3 meter per second. So, this is the condition that Vs1 we are able to find out. Now, once you are able to find out the Vs1, then our next step is to construct velocity triangle. So, to a simplified way of constructing the velocity triangle is to merge both inlet and exit condition in a single graph. So, what we see is that take, because in the both inlet entrance and the exit angle the common is Vb. So, we say that Vs1 comes and this angle is theta, then we have Vr1, this angle is phi, then we have this Vs2 and Vr2, and this angle is delta, this angle is gamma, sorry, this is delta and this angle would be 180 minus delta. So, what we can do, we can drop a vertical from this point and this point and note down as A, B, C, then we have P, R and here we have D. So, from these diagrams we will be now using the trigonometric principles. We have to try to find out or analyze inlet velocity triangle and exit velocity triangle. So, let us concentrate on inlet. So, from this inlet velocity triangle we consider A, D, P. So, we say AD is equal to Br1 sin phi, that is equal to Vs1 sin theta. Again CD is equal to Bs1 cos theta minus Bb, that is equal to Vr1 cos phi. So, these two equations will imply tan phi is equal to Bs1 sin theta minus Bs1 cos theta minus Bb. Similarly, outlet triangle, from this outlet triangle we can find out Pr is equal to Br2 sin gamma, that is equal to Bs2 sin 180 minus delta. Then this means Vr2 sin gamma, if this is gamma, this is also gamma, is equal to Vs2 sin 180 minus delta would be sin delta. Again we have Cr is equal to Cb plus Br, and Cr is nothing but Br2 cos gamma, that is equal to Bb plus Bs2 cos 180 minus delta. So, this will give you the expression Vb is equal to Vr2 cos gamma plus Bs2 cos delta. So, this is one expression Vb. Now, from these two expressions we can also find out what is tan delta. Tan delta would be Vr2 sin gamma divided by Vb minus Vr2 cos gamma. Then we have also working expressions that Kv, velocity coefficient, as Vr2 by Vr1. By using these expressions we will be now insert the values. So, first thing in this problem we will be finding out blade optimum velocity. So, we have Vs1 as 509.3 meter per second. Then we can find out V optimum Vs1 cos theta by 2. So, here theta is equal to 20 degree. So, this will be V optimum would be 239.2 meter per second, 239.3 meter per second. So, once we have optimum speed, then we can find out tan phi as Vs1 sin theta divided by Vs1 cos theta minus Vb. So, by Vb now it becomes V optimum. So, we know theta, we know Vs. So, this will give you tan phi as 174.2 divided by 239.3, this number is 0.728. So, this will give you phi as 36 degree. So, we know Kv as 0.97. So, from this we can find out that Vr2 by Vr1, or we have to find out Vr1. So, Vr1 from our previous expressions we can find out Vs1 sin theta by sin phi. So, this we get from the inlet velocity triangle. So, we know these numbers. So, this is 174.2 because theta we know, Vs1 we know, by sin phi is sin 36 degree. So, this number is 296.8 meter per seconds. Since Kv is 0.97, so this will give you Vr2. So, Vr2 will get as 288 meter per seconds. Now, once you are knowing with Vr2, then we will be able to find out tan delta, because we know Vr2, Vb is known, gamma. So, since the blade is symmetric, so gamma can be equal to phi, that is 36 degree. So, this is due to the symmetric nature of the blade. So, looking at that, we can find out tan delta as 288 sin 36 divided by 239.3 minus Vr2 is 288 cos 36 degree. So, this will give you delta as 88 degree. Once you know delta as 88 degree, then we can say Vs2 sin delta is equal to Vr2 sin gamma. So, we have Vr2 is known, gamma is known, delta is known. So, this will give you Vs2 as 288 sin 36 divided by sin 88. So, Vs2 number is 171 meter per seconds. So, here now we have all the information delta and Vs1, then we need to calculate the power. For power calculations, let me see here work done. W dot would be m dot Vb into Vs1 cos theta minus Vs2 cos delta. So, all the blade angles are calculated. So, part 1 is done. So, part B is work done or power delivered by the turbine per stage. So, here we have all the expressions. So, here m dot is equal to 45 kg per second. Vs1 is 509.3 meter per second. Vs2 is 171 meter per second. Theta is equal to 20 degree. Delta is equal to 88 degrees. So, by inserting these things, we will say W dot would be 5089 kilowatt. Then blade efficiency is, that is part C, is nothing but W dot by m dot into Vs1 square by 2. By inserting this number, we can get eta B would be 87.2%, because W dot we get from this, Vs1 and m dot we already know. Then stage efficiency, W dot into m dot into Hn minus Hs. So, this Hn minus Hs we have already calculated in the first slide. So, where we have Hn is equal to 3043.4 kilojoule per kg, Hs is equal to 2899.3 kilojoule per kg. By putting this, we can find out eta stage efficiency is 78%. So, here all these number W dot we get from this part B, m dot is 45 kg per second, these two numbers we have already found out. So, basically speaking, here in the entire exercise tells us the important fact is that when you calculate this particular term, this cos delta term is either very small. So, in this case this number is about 5 or 6, this may negligible with respect to this, or it will be delta value will be such that it will give a substantial, the cos delta will be angle should be such that this negative term becomes positive. This is one aspect. So, this will give the benefit of for maximizing the work. Then other important concept is that the velocity diagram or triangle should be drawn properly, and more or less we observe that in a given steam turbines the blade efficiency or stage efficiency, they if should be in the range of 80% or above. That means, when you are doing this exercise or design the blade and finding this efficiency is not more than 80%, then it will be considered as an inefficient design. So, this is the important thrust point in the design of blades by choosing a suitable blade angles. With this, I will conclude. Thanks for your attention.